We are going to talk about moles. The person that we're going to attribute most of this to is this guy. Well, him actually. That's Avogadro. Looks a whole lot like a mole monster, doesn't it? We've said before that, that moles are very, very small things, or atoms are very, very small things. That there are roughly 28 sextillion atoms in a pen. Now, pretty soon we're going to start doing quantitative calculations on chemical reactions. Obviously, we can't do that if we're going to deal with individual atoms, because the numbers would be phenomenal. Therefore, chemists use a quantity called a mole. And a mole is simply 6.02 times 10 to the 23rd things. It can be anything. You can have 6.02 times 10 to the 23rd atoms, molecules, pigs, students, whatever. Anything. Avogadro came up with the notion of the mole based on some observations that we'll revisit when we do chapter 9 of the gas laws. Basically, what he found was that equal volumes of any gas contain the same number of gas particles. Now that's kind of surprising, but if you really think about what a gas is, the particles are teeny tiny relative to the volume that they occupy. They're so small, in fact, that they have virtually no impact on how much space the gas takes up. They do impact the mass, because they all have different weights. But as far as the space goes, these guys just fly in straight lines until they hit something. You wind up with the same number of particles in a given volume. So he found this. He also found that if he had 22.4 liters of any gas, and then he weighed that the mass that he got was identical to the formula mass of the elemental compound in grams. And we'll talk about this in a moment within the context of molar mass. But that's a very, very useful notion. This is Avogadro's number. Again, 6.02 times 10 to the 23rd. And he kind of does look like a mole. Think about a dozen. A dozen's a number. We can easily conceive what a dozen is. It's 12. 6.02 times 10 to the 23rd is a huge number. 23 decimal places after our 6. It's huge. Quite often we will round this and just use 6.02. That's typical. But again, think about it in terms of being nothing more than a very large dozen. A mole of bagels would be 6.02 times 10 to the 23rd bagels. Just like a dozen's 12. There would be 5 times 10 to the 22nd dozen bagels in a mole. Okay. Let's do a silly problem. Let's say we had dogs, and these dogs all had 4 legs. So we have 66 dozen 4-legged dogs. How many legs do we have? Okay, well, we can do this. Let's think about this in terms of our given, our ratio, and what we're trying to find. We are given here that we have 66 dozen 4-legged dogs. And we know a ratio. We know that there are 12 things in every dozen. So we can start off just by saying our given here is 66 dozen dogs. We know that there are 12 things in every dozen. And there are 4 legs on every dog.
Thank you.
So I can cancel dozen, I can cancel dog, and I'm left with legs. 66 times 12 times 4, 3,168 legs. All right, well, that's a silly problem, but let's change it just a little bit. Let's say, how many legs are there in 66 moles of 4-legged dogs? That was going to be the same problem, except instead of 12 things in a dozen, we're going to say there are 6.02 times 10 to the 23rd things in a mole. Just a different ratio, but the same concept. So, we start off with our 66 moles of dogs. Now, in every mole, we know there are 6.02 times 10 to the 23rd things. And in every dog, we know there are 4 legs. So, moles and dogs cancel. And we're left with legs. Now, if you've got your calculator out, that's a good thing, because we're going to be dealing with big numbers. And every calculator differs slightly in how you enter big numbers and get real answers. So this is worth doing just to make sure that you know exactly how to do this on your particular calculator. So 66 times 6.02 times 10 to the 23rd times 4, we get 1.589 whatever times 10 to the 26th legs. Now our significant figures here are limited by the number we used here, 6.02, that's 3 significant figures. Remember, 4 legs per dog is an exact number. They're not approximately 4 legs on a dog. They're exactly 4 legs on a dog. So, we round this to 1.59. Any question on the concept? It's just a very large number. We have a mole of hydrogen gas and it has 6.02 times 10 to the 23rd molecules. If we have half a mole, how many molecules do we have? Now again, it's a trivial problem. All we're going to do is say we have a ratio. 6.02 times 10 to the 23rd molecules per mole. And we have a given of half a mole. So we plug in our given. There are 6.02 times 10 to the 23rd molecules in a mole. Our given has units of mole. So in our ratio, mole must be in our denominator. Moles cancel. And our answer is simply 0.5 multiplied by 6.02 times 10 to the 23rd. This would be 3 times 10 to the 23rd. Again, you could have done this in your head, but just remember when you do these big numbers, you're working on the coefficient here, not really the exponent. Any questions? All right, let's take the concept of moles and apply it to what we're going to call a mole ratio. We've talked about chemical formulas, CO2. This tells us we have 1 atom of carbon and 2 atoms of oxygen, right? That's what the formula means. If we had a mole of CO2, how many moles of carbon would it contain? Well, 1. And how many moles of oxygen would it contain? Well, 2. It's the same as the formula. So we could say the mole ratio of carbon to oxygen in CO2 is 1 mole of carbon to every 2 moles of oxygen. If we had ethanol, CH3CH2OH, if we had 1 mole of ethanol, how many moles of carbon?
1.
Just no, look at the formula. We have 2 carbons.
Oh, the whole thing. Okay, I'm sorry.
We have 3, 4, 5, 6 hydrogens and 1 oxygen. A simple mole ratio based on the molecular formula. All right, very quickly, if I tell you we have something with 2 moles of iron and 3 moles of sulfate, what's the compound?
Iron sulfate. Iron 2, sulfate 3.
We have 2 moles of iron, 3 moles of sulfate. Remember, sulfate's just a lump. Okay? That means we would have 2 irons and 3 sulfates. In 1 mole of this, how many moles of sulfur would there be? 3. We have 3 sulfates. So every sulfate would have 1 sulfur. If we had 3 moles of carbon, 2 moles of oxygen, 6 moles of hydrogen, well, exactly the same. Our formula would be 3 carbons, 6 hydrogens, and 2 oxygens. If we had 1 mole of this stuff, we would have 6 moles of hydrogen, we would have 3 moles of carbon, 2 moles of oxygen. This is the concept of the mole ratio. All right, so how do we use this? We're going to use this when we're dealing with molecules and we're looking at the various atoms within the molecule. If I tell you we have 1,000 molecules of ammonia, just 1,000 molecules, how many atoms of hydrogen is that? Well, we look and say, our given here is going to be 1,000 molecules of ammonia, right? Our mole ratio tells us that in every ammonia, we have 3 hydrogens. That's our ratio. So we would set it up like this. 1,000 molecules. 3 atoms of hydrogen in every molecule. Molecules cancel. And we're left with 3,000 atoms of hydrogen. Now instead of molecules, what if I just changed it slightly and said we have 1,000 moles of ammonia? Go ahead and calculate how many atoms of hydrogen we have. You do it, I'll pace. The ratio here that we're going to use is going to be 6.02 times 10 to the 23rd molecules in a mole. We also need to say we have 3 hydrogens in every ammonia. So, our given 1,000 moles. How many molecules in a mole? 6.02 times 10 to the 23rd. How many hydrogens in a molecule? 3. Moles and molecules cancel. 1,000 multiplied by 6.02 times 10 to the 23rd. Try this on your calculator, make sure it works. Times 3. You should get about 1.81 times 10 to the 27.
Because you moved the decimal places, therefore 10 over 27.
Right, this is 10 to the 3rd, 10 to the 23rd, that's 10 to the 26th, times 3, that would be 18. 1 more power of 10 gives us 10 to the 27.
So you want us to leave the significant figure as is showing?
6.02, that's our limiting significant figure. All right, say we have 0.05 moles of carbon tetrachloride. How many chlorine atoms are there? Well, we know that in every mole there are going to be 6.02 times 10 to the 23rd. Anything's pigs. And there are 4 chlorines in every carbon tetrachloride. So our given here is going to be the number of moles, 0.05 moles. How many carbon tet molecules are there in a mole? 6.02 times 10 to the 23rd. And there are 4 chlorines in every molecule.
1.20.
0.05, 6.02 times 10 to the 23rd times 4, 1.204 times 10 to the 22nd. We are at 3 significant figures. Oh no, I'm sorry. Oh, that's right, 3 significant figures, 1.20.
Is it 10 over 22 changes? Because decimal places are not moving anywhere. Is this supposed to stay?
Well, we have 10 to the minus 2 here. We have 10 to the 23. Then we have 5 times 6, that's going to give us 1 more. And then times 4,
but decimal places are not moving anywhere.
No, no, this is right, I think.
Oh,
All right, what if we changed it around? And I said there were 3.27 times 10 to the minus 9 moles of a gas. How many particles of gas are there? It could be molecules, could be atoms, doesn't matter. Particles. Our given here is going to be 3.27 times 10 to the minus 9, right? We're going to have to stick in the Avogadro ratio. 6.02 times 10 to the 23rd things in a mole. So we know how many moles. We know the ratio, things per mole. All we have to do is string them together. Here's our given. We must have moles in our denominator. Moles will cancel, and we're left just with particles. Now deliberately, I wrote this out as moles, and this is MOL. You will see moles written as moles, as MOL, or as MOLE. It's all the same thing. All the same thing. So, 3 times 10 to the minus 9 multiplied by 6 to the 23. We multiply, so we're going to add our exponents, multiply our coefficients, that'll give us another power of 10. We should get 1.97 times 10 to the 15. Any questions? All right, let's look at a simple online tutorial. We have, what is this stuff? K is potassium. What's in O2? Nitrite. Nitrate is the parent in O3. Nitrite is in O2. I was told that this sample of potassium nitrite has 1.11 moles of potassium. That's how many moles are in our sample. How many moles of potassium nitrite do we have? Now this is really simple. What you have to do is simply look at your compound and do a mole ratio. For every mole of potassium nitrite, how many moles of potassium do you have? Well, 1. Now our given in this problem is moles of potassium, isn't it? So when I write my mole ratio, I want to put moles of potassium in my denominator. So, for every mole of potassium nitrate, there's 1 mole of potassium. If we have 1.11 moles of potassium, we must have 1.11 moles of potassium nitrite.
but can you just hold my work? Can you hold it for a second?
Sure. You look at your compound, you do a mole ratio. It's 1 to 1. And you set it up so that the units of your given are in the denominator. Sample of water. We're told water has 1.34 moles of hydrogen. How many moles of water do we have? Well, exactly the same logic here, isn't it? We're going to look at water and say, what's our mole ratio? 2 hydrogens for every oxygen. Now our given is hydrogen. So when we write this ratio, we want hydrogen in the denominator. For every mole of water, there are 2 moles of hydrogen. So that's 1/2.
Do we always put the given in the denominator?
Always. How many moles of hydrogen? 1.34, that's our given. Multiply it by 1/2. We have 0.671 moles of water. Now, when you do this tutorial, when you go online and do this, plug in these numbers. When you click on Show Answer, whether you get it right or not, you will see all of this. It'll all be there. So if you set it up wrong, if you don't get it, you can sit there and do it over and over and over until it makes sense. Any questions?
Did we divide 1.34 to 2?
Yep.
Is that what we did?
That's what we did.
Okay, because I have a 0.667.
Well, you know, maybe.
Just making sure I'm doing the
Um,
concept right.
That's
so
another
that-
thing about the tutorials. There's lots of rounding and significant figure problems in some of these tutorials. JavaScript is not good at that, and I'm not a great programmer. So sometimes little things will show up. Ignore them.
Right.
The answer is set so that there's lots of slop.
I'm only confirming for my knowledge, so I know the system and the technique so that I don't have to get confused.
I understand.
And maybe.
Blackboard is the same way. If you see the same problem on Blackboard, which you might, it is designed so that if you're within 2 or 3% of the answer, you get it right. All right. Going back to our friend Avogadro. We said that if he took his 22 liters, that the mass was identical to the formula mass. Now, what this means is that if we have any substance, anything, any compound, any element or whatever, and we have 6.02 times 10 to the 23rd of those, that the formula mass expressed in grams will be the same as 6.02 times 10 to the 23rd particles of that substance. Formula mass, we'll see, is simply the mass you get by adding up the masses on the periodic table. This is what we'll call the molar mass. For example, carbon-12 is the universal standard for calculating masses. If we had exactly 12 grams of carbon-12, only the isotope carbon-12, then this 12 grams would have 6.02 times 10 to the 23rd atoms of carbon-12. Now we know that carbon consists of different isotopes. The average atomic mass is what you see on the periodic table, and that's 12.01. So if we take average carbon, mixture of isotopes, and we have 12.01 grams of it, that's 6.02 times 10 to the 23rd atoms of carbon-12. Used to define the mole based on volumes and stuff like that. These days, it's simply based on as many particles as there are in exact number, 12 grams of carbon-12. All right, so that's what molar mass means. If I tell you that magnesium hydroxide has a formula weight of 58.32 grams. Now what that means is we go to the periodic table. Magnesium is 23. Oxygen is 16, hydrogen is 1. We add them all up, we get 58. That means that 1 mole of magnesium hydroxide weighs 58.32 grams. Now, I have 17.8 grams of this stuff. How many moles do I have?
17.8 over 58. Okay.
All you have to do here is take our mass, our molar mass, as units of grams over mole, right? So we can set up a simple expression here. Our given would be 17.8 grams. We're going to use our molar mass as a ratio, grams per mole. But we have to set this up with grams in our denominator. So they will cancel. Basically, mass divided by molar mass gives us moles. 0.305 moles of magnesium hydroxide. Another exam problem. A mole has 6.02 times 10 to the 23rd molecules. If we have 10% of a mole, how many molecules do we have? The reason I did this problem is I want you to appreciate what 10% really means. It's a ratio, isn't it? 10 parts for every 100. So what we're going to do is take our given and we're going to multiply it by this ratio, 10 parts per 100. When we do that, we simply move our decimal over 1 to 10 to the 22nd. Now, like I said, this was a real exam question. What's the answer? Well, this is 6 times 10 to the 20, not 22nd. This is stupid. This would be 10 to the 21st, right? That's obviously wrong. This is the dreaded none of the above. All right, we have looked or talked about big numbers here, right? Big numbers, moles. Let's just do a couple things, this one and then one silly one, to try to stress exactly how large a mole is. What we're going to do here, this is a leaf. And we're sitting here about a centimeter above the leaf. What I'm going to do is move back 1 power of 10 every time. So starting off here at 10 to the minus 1 meters, then we're going to go to 1 meter, 10 meters, 100 meters away from our leaf until we get to 10 to the 23rd. All right, now you can see it's a bunch of leaves, or you can see it's a tree now. There's a tree in a parking lot or somewhere. Oh, we're in Florida. We're at 10 to the 7 now. There's the Earth. Here's the orbit of the moon. Here's our orbit around the sun. Oh, and there's the sun. There goes our sun. And we're now 10 to the 18, 10 to the 17 way. Oh, we're up in the Milky Way. This is an arm of the Milky Way. Start to see the arm. Oh, there it is. And finally, 10 to the 23rd meters above our leaf, our galaxy is this little fuzzy ball. 10 to the 23rd is a phenomenal number, phenomenally large. All right, here's the silly version.
Mole is an animal that burrows in the ground, or a spot on your chin that you gotta shave around. But there's another kind of mole of interest to me. That's the kind of mole they use in chemistry. A mole is a unit, or have you heard, containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend. Now say you had a mole of pennies to distribute round the world. Give to each of the 5 billion grown-ups, boys and girls. There wouldn't be a single soul down and out of luck, 'cause everybody in the world would get $1 trillion.
$1 trillion.
Or say you had a mole of paper and stacked it toward the sky. Paper's all thin, but that pile would get so high it'd reach up into outer space. In fact, I think you'd find it'd go up to the moon and back 80 billion times. And the mole is a unit, or have you heard, containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend. Now suppose a mole of marshmallows fell upon the planet. Over each square inch of land and sea, you think that you could stand it? That layer would be 12 miles high and, of course, block out the sun. We're talking close to 5 million trillion tons. Well, maybe we could save ourselves if we all started eating 1 marshmallow each second. Not 2, because that'd be cheating. With 5 billion people munching, how long do you think it'd take? 40 million years, and that's without a bathroom break. And the mole is a unit, or have you heard, containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend. Let's say you had a mole of atoms. Would the pile be immense? Should I say the answer now or leave you in suspense? Well, atoms are so very, very small, you understand. You could hold a mole of atoms in the palm of your hand. So shake a little sugar in the middle of your palm. Now you don't want to spill it, so try and stay calm. You hardly can imagine and barely realize there are more atoms in that sugar than stars up in the sky. And the mole is a unit, or have you heard, containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend.
All right, where do you think Mole Day is? October 23rd. 10/23, get it? Okay. All right, you know, like it said in the silly movie here, if I had 7.5 grams of the amino acid glycine in my hands, it would be a little pile like this. This contains 1 mole of atoms, 6.02 times 10 to the 23rd atoms. Now, how do we go from glycine to moles? Again, this is the concept of molecular weight. As I said, formula weight, if you take a compound and you look and see what it's composed of, then go to your periodic table and get the masses. You can come up with what we call the molecular weight. For glycine, the molecular formula is C2H5NO2. Now, if we wanted to get the molecular weight of glycine, again, we would go to the periodic table. Carbon weighs 12, hydrogen's 5, nitrogen 14, oxygen 30, well, 16 each. And we would write it out like this. We have 2 carbons at 12, 5 hydrogens at 1.008, 1 nitrogen, and 2 oxygens at 16. Multiply, add it all up, 75.07. Now that's the molecular weight of glycine. The units are actually atomic mass units. Nobody ever writes atomic mass units, abbreviated AMU. But, according to Avogadro, if we had 75.07 grams of glycine, we would have exactly 1 mole of glycine molecules. So you look at your compound, you add it up, get the molecular weight, express it in grams. The units are grams per mole. That's our molar mass. Now, think about this concept. This balloon, it's about 1 foot. It contains 32 grams of oxygen. That's 1 mole. This little lump of copper down here, 63 grams. That's 1 mole of copper. 18 grams of water. Looks like this. That's a mole of water. Calcium carbonate, chalk. Remember when they used to use chalk? That's 1 mole of calcium carbonate. Now, why is this going to be important to us? Well, because if we wanted to react 1 mole of copper with 1 mole of oxygen, we could do that by simply taking 63 grams of copper and react it with 18 grams of oxygen. Both of those contain the same number of molecules, don't they? And so that's how we're going to do what we call stoichiometry. Stoichiometry is a wonderful word. You can say it to your friends, they'll be so impressed. We'll do this in chapter 6. All right, let's say that I have 21.509875 grams of CO2. And that if we add up the molar mass of CO2, it comes to 44.01 grams per mole. I want to know how many moles of CO2 I have. Well, we can do this. Our molar mass is 44.01. To get our moles of CO2, we simply need to take our the number of grams, that's our given. We're going to use our molar mass as a ratio. Now our given is grams, so we must invert this so gram is in the denominator. Here's our given. Here's our molar mass flipped upside down so that grams can cancel. Now I do my calculation, and I hope you've done it on your calculator. And you get a number that looks like this. The whole point of this exercise is that this number, if your calculator is working right, should end in exactly 5. Exactly 5. Now, we have 4 significant figures, right? So we have to round this. How do we round this to 4 digits?
4889.
Do we round up? 88 it would be. Or do we round down to 87? Doesn't matter. Of course it matters. There's a rule. If it ends in exactly 5, you round so your number is even. Because of that, half the time you round up, half the time you'll round down. And so that's fair. So the point of this problem and this very large number was to make sure your calculator spit out a number that ended in exactly 5. If that happens in a calculation, remember, you round even. If this had been 5.001, we would have rounded up. But if it's exactly 5, you round only even. All right, on an exam once, I gave this little table and I gave this problem. Pretend you're taking an exam. I have 1.03 moles of methane. That's carbon tetrachloride. Calculate the mass of 1.03 moles of carbon tetrachloride. Well, all we have to do here is simply add it up, don't we? Methane is going to be 1 carbon and 4 hydrogens. That's going to give us grams per mole. We know how many moles we have, so we can get grams. Our molar mass, we have 1 carbon, 4 hydrogens. We're at 16.04 grams per mole. Our given here is 1.03 moles. So this ratio we use must have moles in our denominator. Here's our given. We have to set it up with moles of methane down here. That's grams of methane up there. That'll be 16 grams per mole. Our moles will now cancel. We simply multiply it out, and we get a huge number. But we're working with 3 significant figures, so we round this to 16.5. So, let's say that you were doing an experiment. And in this reaction that you were going to do, you needed 1.03 moles of methane. By this simple calculation, all you have to do is weigh out 16.5 grams of it. And that will be exactly as many particles as in 1.03 moles. Now that's kind of neat, isn't it? All right, this is a very simple tutorial, tutorial number 2. All that you have here is a table, and you have to fill in the missing amount. We are given a mass, we are given moles, and I want you to calculate grams per mole. Well, this one is exceptionally easy because molar mass is grams divided by mole, isn't it? All we have to do is take our grams and our moles and divide them. When we do that, 1.04 or 104 divided by 1.03, we have 100 grams per mole as our molar mass.
We need to put the dot in the end of the 100.
Well, you see, why did I have to put that dot there?
Yes, please.
It came out exactly 100, didn't it?
No, we did not.
Well, the 3 significant figures it did. Came out 3 significant figures at 100. How can I tell the world that this value really is good to 3 significant figures? That's a problem. It is. So, one way you can do it is to stick the little dot. Looks stupid, but it works. Another thing is called an overbar. Sometimes you'll see this in books. They'll write a line above all the significant figures. But whenever you have a significant number with zeros at the end and no decimal, it's tough to express it. It is. So you have to be a little imaginative. Try this one. Here's our molar mass. There's our moles. How many grams are we talking about?
When you write it, you do 3 significant digits.
This is all you have to remember, is that mass divided by moles is molar mass. Now here we're given molar mass, we're given moles. If I simply take molar mass multiplied by moles, I will get my mass. So I substitute in, and it's 163 grams. Let's say I have 87.36 grams of copper. How many moles is that? Wait a minute, we look at our periodic table. Copper, the molar mass is 63.5 grams. Right? So, we know our molar mass. We know our mass. Again, moles times molar mass. Now we're trying to find moles, aren't we? Molar mass divided by, well, let's see, blah, blah, blah. Let's swap this way. This way, mass divided by molar mass is moles. That's one of the things that you say before you go to sleep at night. Mass divided by molar mass is moles. Everyone promise you'll say that before you go to bed. Mass divided by molar mass is moles. Mass divided by molar mass, we plug in our numbers. This is 1.38 moles. We have 0.23 or 0.243 moles of lead. What's our mass? If 1 mole of lead weighs 82 grams, 0.24 moles of lead, simply moles times molar mass gives us mass. All we do is plug it in, and we've got 19.5 or 19.9 grams. Now here's a cute one. We have a sample of an element, and it weighs 29.14 grams. Okay? Don't know what the element is. But we know, somehow, that this contains 2.698 moles of that element. What's the element? All we have to do here is figure out the molar mass of the element. Then we look at our periodic table and try to match it. Our molar mass is going to be mass divided by moles. We have 29 grams, we have 2.7 moles. We divide them together, 10.8 grams per mole. That's our molar mass. Then you look at your periodic table, and we're looking for about 10.8. 10.81, by gosh, it's boron. Any questions? All right, this was an exam question. It was actually an extra credit. Had to show all your work. You were told you had 2.3 times 10 to the minus 4 moles of sodium chloride. How many atoms of sodium are there? Now, you know, this really isn't difficult for 5 points. We know how many moles we have. We know how many atoms there are in every mole. And we know the mole ratio, that's how many sodiums per sodium chloride. All we have to do is string together those 3 ratios. So, let's do this math, and you guys can fill in the ratios. Let's start with moles. Go to number per mole, number per formula unit, that's sodiums per sodium chloride, and wind up with atoms. Our given here is going to be 2.3 times 10 to the minus 4, and here's our two ratios. Fill them in. All right, number per mole. Our given has moles in our denominator. I'm sorry, our given has units of mole. So we want moles in our denominator here, don't we? We want the number of sodium chlorides in 1 mole of sodium chloride. Remember, we have to use formula unit because it's not a molecule. And that's just Avogadro. 6.02 times 10 to the 23rd per mole. Now, number per unit. This simply says how many sodiums per sodium chloride. Well, that's so simple I can do it. 1 sodium for every sodium chloride. Sodium chlorides will cancel, and we're left with atoms of sodium. What's the answer? This is a calculator answer, 1.38, blah, 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 10 to the 20. We have 2 significant figures. So we round this to 1.4, whoops, times 10 to the 20. Yeah.
So you basically just multiply the 2.3 times the guy's number, right?
Mm-hmm.
I forgot his name, the Molar.
Avogadro. How could you forget somebody like Avogadro? You should have nightmares about Avogadro.
What color that avocado number?
But you wouldn't give us the wrong, if we put 1.38
For the extra
for the
credit?
next one. If we put 1.38.
Well,
I see it wrong to even.
you know, maybe 4.97 points out of 5. Okay. All right, let's say I have 10 to the 20 molecules of chlorine. What's the mass of my sample? It's the same mole exercise, isn't it? If we have 10 to the 20 molecules, we have to figure out how many moles that is. If we know how many moles that is, then we know how much it weighs. We know the number of molecules. We know molecules per mole. That's Avogadro. And we know the molar mass. We are given 10 to the 20 molecules. We know that there are 10 to the 23rd molecules in every mole. Molecules is in our denominator. We know that every mole weighs 70.9 grams. We're left only with grams. We have 2 significant figures, so this is 0.012.
You go back for a second.
I'm sorry?
Then going back just for 1 second.
Remember, well, I dearly hope that the recording is working. It didn't work in the other section, so this is our last shot. So I really hope it's working. All right, we have 0.2 grams of CO2. How many atoms is this? Same problem. We are given the number of grams. We know how many grams there are in a mole. That gives us how many moles. We know that every mole is going to have 6 times 10 to the 23rd things. And every CO2 is going to have a total of 3 atoms. So think about how you would set up your ratios. You're going to start with your given. Grams is in our denominator, so we want to take this, put grams in our denominator. That'll give us moles. Then we need Avogadro's number, and then we need 3 atoms per CO2. Grams to moles. Going to take our molar mass ratio here, going to flip it upside down, so grams cancel. To get moles into numbers, we're going to use Avogadro's number with mole in our denominator. And finally, we know that in every molecule we have 3 atoms. Now we just multiply all this out. And again, please do this on your calculator, the one you're going to use on exams, because this is one of the string operations that you need to be confident in. 0.2 divided by 44 times 6.02 times 10 to the 23rd times 3. 8.207 times 10 to the 21. 2 significant figures, 8.2. Any questions? Well, let's go ahead and look at the 3rd tutorial in the chapter. And then we're going to come back and we're going to talk about ratios and proportions and finish up. Let's say we have, what is this? Lithium nitride. Very good. And it has 1.9 moles of lithium. How many grams of lithium nitride are there? Well, we need a mole ratio here, don't we? Every mole of lithium nitride has 3 lithiums. So our ratio is 3 to 1. We are given moles of lithium, so we have to set that ratio up with lithium in our denominator. So our ratio is going to be 1 divided by 3. Now, we are given moles of lithium. So we're just going to multiply our given by our ratio. We wind up with 0.633 moles of this stuff. Now I did 2 steps here at once. Once we know we have 0.633 moles of this stuff, all we have to do is to take the number of moles, multiply it by our molar mass, which was given, and we get 22 grams of our compound. Do another one. We have a sample with 0.598 moles of, what is this? This is trickier than the other one. It's a cobalt oxide, isn't it? What's the oxidation number? Every oxygen is going to be a -2. So there's 6 negatives. That means every cobalt must be +3. Cobalt 3 oxide. All right. How many grams of cobalt do we have in this sample? Our mole ratio, 2 cobalts for every cobalt 3 oxide. Right? We are given moles of cobalt 3 oxide, so that has to be in the denominator. And our ratio is 2 to 1. Now, we are given about 0.6 moles of this stuff times 2 gives us 1.19 moles of cobalt. We know that every mole of cobalt weighs 59 grams. We have 1.19 of them, so we have 70.7 grams of stuff. One more. We have C2H4O. It has 4.24 moles of carbon. How many grams of this stuff do we have? Well, every C2H4O has 2 moles of carbon, doesn't it? So what's the mole ratio? 2 to 1. We have given this carbon. So carbon has to be in the denominator. So we will use 1/2. We are given so many moles of carbon. Going to multiply that by our 1/2, so that divides it by 2. So roughly 2.1 moles. Finally, we know that every mole of this stuff weighs 44 grams. We have about 2.1. 2.1 times 44, 93.4 grams of stuff. All right, this is a lot on your head, I'm sure. Probably need to go put your head under the water fountain for a minute or two, so we'll take a quick break.
You're doing a tutorial for section 4?
Hmm?
4.
This is chapter 4.
No, the tutorial.
So,
The tutorial online.
oh, that's right.
This is 3.
This is the 3rd tutorial in chapter 4.
This is the 3rd tutorial.
In chapter 4.
It's like the 4th tutorial.
That's going to
You
be
doing it though?
just a moment.
No.
But we all get to relax for a minute first.
I don't know.
Ah.
They don't understand my Took it, failed. Took it again,
So
failed.
here's my never-ending
I took it again,
questions.
got a C.
So as I was checking the quiz, I feel like this question is missing a chart. Because of that, I couldn't get the
Oh
question.
my lord.
It's a neutral element,
I'll let you know.
that means it's neutral, no charge. That's why.